Okay, welcome back, ladies and gentlemen, and tonight we're going to be talking about using quadratic key features in real-world problems, and that's going to be problems like where a basketball is thrown or a football is thrown or any kind of projectile. Could also be talking about height versus time or any kind of real-world situation that models a quadratic curve or parabola. Now, really what this is about is interpreting these key features. So we have to interpret key feature points on the graph and what they mean in the real world situation. So what we need to do is interpret these key feature points. Okay, we're going to be looking at points and where we use these points. So tonight we're going to be looking at 3 word problems, 3 models that use this, okay? So let's look at our first one here. And it's probably going to be a little small on the video, so I will read it to you. Okay, but this is a great example of a key feature problem where it's going to ask you to interpret a key feature. And this one says, the path of a basketball after it has been hit is modeled by the function h equals negative 0.0032 d squared plus d plus 3, where h is the height, okay, h is the height in feet of the basketball, d is the distance in feet of the basketball, okay, from home plate. What is the maximum height reached by the baseball? Sorry, I'm talking about basketball. This is all about baseball. And how far is the baseball from home plate when it reaches the maximum height? So we've got 2 questions. We want to know what is the max height and what is the distance at max height. Okay, so again, it's asking what is the maximum height reached by the baseball and how far is the baseball from home plate, that is what is the distance, when it reaches this point at the max height. So we're talking about the same point, but it wants to know specifics about this point. So what we're going to do, of course, is graph it because we want to see what this trajectory looks like. And so, of course, I have my handy-dandy Desmos here, and I have graphed. Give it a second to kind of get used to the brightness. I have graphed this function, and this is kind of what goes up. And you can see up here, negative 0.0032 x squared. What I did was I changed the variables to x, so it would graph. Okay, there's a couple ways to graph. This is one of the easier ones. You all understand x, and so does Desmos. So I just graphed it, and what we get is this thing that looks like a straight line. But don't be fooled, okay? Always check before you think there's something wrong. So when we zoom out here, it starts to curve as you zoom out, and then you can kind of really see what we need to look at. We need to look at this section right here. And again, when we tap on this guy, these gray dots, we're going to get 1, 2 really close over here. And then you're going to get 1 up here at the top and 1 here. And we want to know first, we're looking for the max height. That's what we're looking for. So here, I'm going to go back, give it a second to kind of adjust. Okay, I'm going to go back and I want the maximum. And that's the highest point on there. If you remember your key features, the maximum is the very highest point. So right here. So really, my maximum, and I'm going to write here, I'm going to write the max point is, and off of Desmos, it's telling me the maximum point is 156.25, 81.125. Okay. Now, I'm going to draw just a quick representation of this graph because I want you to see kind of what we're talking about as we discuss. So let's move down a little bit, and we're going to draw just a quick representation of this graph. So here it comes. And if you remember, in this real world problem, we got three really important points. There's, of course, there's another x-intercept over here, but that one's before it started, so we're not worried about that one. Okay, and it's said in the problem, this x, okay, or the d, is said that's distance traveled from the base, and then this is height. Okay, it gave you that information in the word problem up here at the top. All right, and so this point is our 156.25, comma, 81.125. And again, it also tells you that this is in feet. Distance in feet, height in feet. Okay, so we're looking for the maximum height. What is the actual height? The max height, the highest point, or the highest the baseball gets. Okay, so we know this point is really two numbers, an x and a y, or in this case, a distance and a height. So to answer our first question, the max height is going to be 81.125 feet. Why is that? Because that's this point over here on the height. It's actually the y value. That's the maximum height. The second question is, what is the distance traveled at max height? So you're still talking about the same point. If you look here, the distance is this point. It's the x value. So if this is 81.125 feet, then the distance is going to be what? 156.25 feet. Okay, so a lot of people, a lot of students are really ready when we say maximum, because we've drilled it in, to say, well, the max height is 156.25, comma 81.125. And while that's technically true, we're asking for a maximum height, and a point or Cartesian coordinate point is not a height value. That's a point on a graph. Okay, what we want to know is actual height value. So you have to be able to pick it out. Is it the 156 or the 81? And in this case, it's the y value. And that means that the distance traveled when we're at 81 feet high, the ball has traveled 156 feet from the plate here, from the starting point, 156 feet. Okay, so that's how you answer that question. All right. Now let's look at another example here, because we want to keep this ball rolling. Okay, let's look at another example. Let's see if I zoomed in too far. Oh, just perfect. Okay. So, suppose you are tossing an apple to a friend on a third-story balcony. After t seconds, the height of the apple in feet is given by this equation. H equals negative 16t squared plus 38.4t plus 96. Your friend catches the apple, and just as it reaches its highest point, how long does the apple take you to reach your friend? How long does the apple take to reach your friend, and at what height does the ground, above the ground, does your friend catch it? Okay, so how long does the apple take to reach your friend? And at what height above the ground does your friend catch it? So we've got two questions. We're talking now about how long and what height. Okay. Now if you read the situation again, it says you're tossing an apple to your friend on a third-story balcony. Here's the equation that models that. Your friend catches the apple just as it reaches the highest point. Okay, so this is what's telling you where to look. Right here, we're looking at the highest point. Okay, so what do we need to do? Well, we need to graph it. So I'm going to pull out my handy friend Desmos. Okay, again, you can also graph it on the TI Inspire. Okay, and I'm going to graph the equation that we were given. Negative 16. Our equation says t squared. I'm going to use x squared plus 38.4x plus 0.96. Okay, so we get this tiny little, because we're still zoomed in from our last one. So I'm going to hit this home button, and it'll kind of zoom in real close. And we can zoom out, and if you're really careful about pulling horizontally, you can actually modify this graph so it stretches one axis at a time. Okay, and so there we get a really nice parabola looking at this scale on y and this scaling on x. All right, and so again, if we tap it, you can see all the important points. I've got my x-intercept down here at the bottom, and then my y-intercept just above it. Okay, and then up here, I've got my maximum and my other x-intercept. Okay, but really what we're looking for right now is the highest point, this right here. All right, so let's go back, and we're going to draw kind of a representation of that graph, because that's the one we want to look at. So let's draw it. Okay, and this is just the first quadrant, okay? Just the part that matters, the starting point, the highest point, the other x-intercept, where this apple would hit the ground if it wasn't caught up here. All right, and it tells us this point here is 1.2, comma, 24. But the word problem also tells you something, okay? It tells you, look at the t inside the equation, the t being the squared term, that's down here. T represents time. This time in seconds, okay, and here, h, my y-axis, or my h here, the h represents height, and I can't spell like normal, in what? Height in feet, it's right there. Height in feet, okay. So, here, we're asking how long. How long does it take, or how long does it take the apple to reach your friend? And our friend catches it at the highest point. It catches it right here. But we want to know how long. So if I'm asking how long, would I say, how long does it take to reach your friend? Oh, it takes 24 feet to reach my friend. Is that a how long? Is that a time reference? No. Okay, so when we answer that first question, how long, we're going to say it takes 1.2 seconds to reach our friend. Why are we saying 1.2 seconds? Because that's my x value. Okay, that's the time. It's asking for a time. This is how long does it take. Okay, and feet is not a time measurement. So 1.2, the x value, is how long in seconds it takes that apple to go from here to here. Okay. The next second is at what height? The next question was, at what height does your friend catch it? Okay. And remember, it says our friend catches it up here at the highest point. How high is that? Well, that's my y value, okay? That's the feet over here, the height. All right, so our friend catches it at 24 feet. Okay. Our friend catches it at 24 feet. Right there, 24 feet and 1.2 seconds. So it's really interpreting what this thing means. Okay. Now, for the last example, I've got a few questions on this one because I wanted to see more than just the height. Most quadratics really love to ask you about the max height because that's a really important point on these quadratics. But sometimes they can ask you about other things. So here we've got kind of a mixture. It's going to ask us about three things given this information. Okay, and in this it says a water balloon is catapulted into the air so that its height, h, in meters, after t seconds is h equals negative 4.9 t squared plus 27t plus 2.4. Okay, so there's a situation. And before I do anything, before I read any of these questions, because we've got about 3 questions here, I really want to get a hold of the situation. So I'm going to graph it. Why? Because graph everything when it's asking about key features, height, how long does it take, where does it hit the ground, graph it. That's the best way to get a visual. So here's our old graph. We're going to get a new one. Okay, the new one is negative 4.9 t squared. Remember, I'm using x here. Okay, if we don't name our graph h of t, then it won't know what t means. So we can just change that to x. Negative 4.9x squared plus 27x plus 2.4. Okay. Ooh, make sure you get 2.4. I just did 24. All right. So here is my graph. And then I can hit return on that and zoom out so we get a nice pretty parabola. Look at that thing there. It's a very nice parabola up and down. So we're going to tap again and it'll give us all the important points. Oh, that looks a lot better. We're going to tap again and give us all the important points. There's my x-intercept, this one right here, but it's not really in the situation because it starts up here at the y-intercept. Okay, so we're not going to worry about this guy. We're just going to look at this guy. And then up here we have the maximum, or the vertex. Remember, that's also called a vertex. And then down here we have the x-intercept again. So I'm going to draw the situation getting all of these points labeled because I just want to know everything about this. Okay. So we're going to start a little bit above. It's going to go up, and then it's going to come back down. Cool. And these are the 3 points I really think I care about. We'll see if it's asking for anything else. So 0, 2.4. This is 2.755, 39.594. Sharpies don't really help when you're trying to write small. Not a problem. And then this guy down here is 5.598, 0. Okay. And that's a 39.594 up there. All right. So here, we've kind of drawn and labeled. This means right here, we start at how high? 2.4 feet high. Okay, that's our y-intercept. And then the maximum height. And then here we've hit the ground. So that's the maximum distance. The farthest it traveled, or I'm sorry, the farthest time, the longest it took to hit the ground. So how high is the balloon after 1 second? That's not really any points here, okay, because this is 0 seconds, and then here we have 2.755 seconds. Time is right here. This is 5.598 seconds. So how did we get that? Well, I go right back to my graph. Here's my graph. Zoom in so it kind of lightens up for it. All right. And I want to know 1 second. Well, at 1 second, as I'm pulling my finger along this, the seconds are ticking up. And right about there is 1 second. Okay, y'all kind of have trouble seeing this. Let's see if I can get it. See it, and as I move along the graph, 0.9, there's about 1 second right there. It says 1 second. Oh, I just had it. 1 second, 24.5. Okay, so let's label that guy on our graph. Here, I'm at 1 second, and I've got 24.5. Cool. All right, so how high is the balloon after 1 second? Well, after 1 second, the y value, the height, is 24.5 feet. There is my answer. Okay, and if I'm being nitpicky, yes, you should definitely include the measurement of distance, okay, the feet. Next question, what is the maximum height of the balloon? Well, luckily, since we know that's a really important point, we've already labeled it. The maximum height, the maximum occurs right here. And the height at this maximum is the y value, okay, our y value. That's 39.54 feet. .594 feet. Okay. And last but not least, okay, when will the balloon burst as it hits the ground? So really we're looking for when does it hit the ground. Okay, just describing what it does when it bursts. And when does it hit the ground? Well, we've already discussed that. It's right over here. Okay, this is the point where it hits the ground. And at that point, it's traveled for how long? The x value along the bottom is 5.598 seconds. Okay, so when does it hit the ground? At 5.598 seconds. All right, and there we go. That's interpreting key features in real-world situations. All right, as long as you follow what your x and y axis should be labeled, you should have no problem. Have a great night.